One of the most interesting concepts in understanding the vector calculus is the curl. Okay, talking about the curl, the thing that comes in our mind is the conservative and non-conservative fields. And we can start it by, we can start understanding it using the electric field. For example, as you know, that for a static charge, the conservative field, the electric field is actually conservative field, right? So, what does Maxwell's first equation says is that the curl of the electric field would be zero for for a conservative electric field, right? What does it mean is that if the charge is throwing out or radiating the electric field in all the directions such that the charge is static and has zero acceleration and velocity, then in that case the nabla of electric field would be zero. The question is that from where does it come from? Well, it comes from the curl. Okay, now the question again arises that from where does the curl come from? So it comes from the Stokes theorem. So the thing actually lies in the Stokes theorem. So now let's connect it with the maths. So the theorem says that the line integral of the electric field dot ds along the del s is equivalent to the double integral of nabla dot e dot da. Why does it come to be zero? Think for the case of conservative force. As we know that for conservative force, F dot dr, that is the work done, is always equivalent to zero. We often say it for a closed loop. That is only the case for electric field also. The second question arises is that how do we exactly deal with it? Right? How do we exactly deal with it? So let's start from the very top. So the main question is that what does it mean for a field to be conservative? As we have already discussed that the answer lies in the curl, right? The second question arises that what does the curl mean and what is its practical intuition, right? In general, as we all know that the curl measures the rotational effect of that vector, right? If the curl is zero, that means that it's producing zero rotational effect, right? If the curl is zero, in that case it's producing zero rotational effect. So by Stokes theorem, I can say that, for example, if I am integrating electric field, then E dot dr is equivalent to the double integral of the nabla of E dot da along the surface S through delta S. Okay, this is Stokes theorem. So, as I know that the electric field is conservative for a static charge, right? For a static electric field, it's always conservative. So from this side, I can say that on the left side we have the circulation of the electric field around a closed loop, and on the right side we have the flux of the curl through the surface. So I can say that if the curl is zero everywhere, then the line integral is also zero, right? And that is exactly the condition for the field to be conservative. That is the main condition for the field to be conservative. Hmm. That this line integral must be zero. So in order to make it zero, we take this curl as zero. And this is the point where it gets connected towards vector algebra. And now the next point is to analyze the curl. What does the curl, what's the practical intuition of curl? If we'll see there, then through an animation, if we will see here. So basically the curl. Okay, so what we are seeing right here is the conservative force. As we know that if if the curl is zero, the force is conservative, right? This means there is zero rotational effect. Now, if the curl is not equivalent to zero, in that case, it's non-conservative force, right? And it's and it has some rotational effect or maybe a lot of rotational effect. Right. So let's see it. What does it exactly mean for a rotational effect? So we are starting from conservative force. Although as we can see there that in Harvard's website they have given, and Harvard has explained it very well. And like this is the conservative force field. Okay, these are the conservative forces, and the thing that is to be noticed is that for the red arrow you can see that the size are much smaller than the blue arrow. So it doesn't matter that what is the size there. The thing that matters is that is it creating a rotational effect to this paddle wheel which is rotated there. I don't think so that it's creating a rotational effect. Does it look? No, this is simply passing through it. So therefore we can conclude that the rotational effect is equivalent to zero. So this is a conservative field. We can understand it by this definition also, by this animation also. Okay, so yeah, as in the conservative field you can see that the net rotational effect is equivalent to zero, right? But in case if we get into a non-conservative field you can see that the paddle is rotating, right? Look, this arrow is causing the pedal to rotate. It's not just passing through the corners, right? And yeah, in this case also doesn't matter the strength of the electric field, I mean the conservative field at every point can be different, and these conservative forces or any conservative vector whatever you called it can be different, right? The thing that matters is that whether it's creating a rotational effect or not to these paddle wheels. So yeah, and you can see there that this is totally rotating this is the main point to get it. So this is the point from where we can connect it again to the Stokes theorem. So as Stokes theorem says that the net line integral is equivalent to the nabla cross E dot dA. Yep, double integral. From there only we can connect it that once every closed loop integral is zero, something very important follows. What is this? So basically, the work from point A to point B does not depend on path, right? So this means that the field can be expressed as a gradient of some vector or maybe some scalar potential. So from this point only, we come towards the conclusion of E is equivalent to the nabla V, right? And this is why we talk about the electric potential or voltage in electrostatics. So the math of curl directly explains why we store energy in the field as potential energy. Okay, so yeah, this is the example. So talking about the example of conservative field, we come to Coulomb's law, and which says that the electric field is equivalent to k q1 q2 by r square. And yeah, this is only valid for the static charge, right? This is only valid for the static charge. And it also says that from this definition that it does not cause any rotational effect to that pedal. The divergence is equivalent to zero. Sorry, I mean the curl is equivalent to zero, which is nothing else but Maxwell's first equation, right? So this is nothing else but Maxwell's first equation. Sixth is basically that we all know Faraday's law. And this is the one of the point that is to be noted that not all electric field are conservative, and in case if it is causing a rotational effect, as you can see there, yeah, this is causing a rotational effect, right? The paddle wheel is rotating. What is the example? The best example is Faraday's law. Faraday's law says that the nabla cross A, that is the curl, is not zero, right? In general, not always, yeah, but in general. So it gives del B by del D, right? Um, so as you know that when the magnetic fields are changing with time, this is what the Faraday's law tells us, right? So yep, this is non-zero, and the pedal wheel spins in this case like this. Okay, so this is the case where you can also tell that the closed integral of E dot dr is equivalent to minus d phi b over dt. Okay, and that's exactly when the induced EMF in a loop depends on the, you can say, yeah, on the path. Okay, notice this thing again. This is nothing else but along the integral along the line. Okay, so yeah, so here's the complete picture that in electrostatics the curl of E is basically equivalent to zero, right? I mean for the static electric charge, and the field is conservative, potential exists, energy stored. In electrodynamics, when the magnetic fields change with time, the curl of E is non-zero. That is to be noticed. The field is non-conservative and the potential fall and the induced EMF appears. So in short, we can tell that the curl is the master key. It tells us whether the field is conservative or not. Okay, the curl again, the same thing, the rotational effect that we can see here. Okay, so yeah. So this is the deep meaning of saying that the electrostatic field or any other field is conservative. Okay, this pedal effect decides that whether the field is conservative or not. Okay, uh, yeah. So this was all about, I mean, the basics about understanding and getting that what exactly happens and when it get connected. Okay, thank you.